Okay, well, thank you very much for the invitation. It's a great pleasure to be here. So I'm gonna talk about something a little bit more down to earth than a lot of things. So I want to investigate the following situation. So okay, so here is what I want to talk about. Let's have a family. A smooth projective family, and I want to investigate the following thing. So let's look at the Noether-Lefschetz locus of pi. So this would be the set, maybe of geometric points. Let's say set of closed points of S or something like that, such that the Picard number of the fiber at S is strictly bigger than this. So this is the rank of the Néron-Sévry group, and eta bar is maybe a generic geometric point of the base. So the situation that I want to investigate, so in concrete terms, we have a family of varieties. We look at divisors on the fibers. Well, we certainly have those that extend, that extend to the whole family, maybe after some ramified base change, okay? And well, we have the Noether-Lefschetz locus, which corresponds to these exceptional points of the base where we have an extra line bundle that doesn't deform over the base. So here is a prototypical theorem that I want to recall, and I'll give a very short proof. So this is due. So this has been proved independently by a number of people. So I think the first proof was by Mark Green, and Keiji Ogiso gave actually the same proof, and then there is a different proof by Borchertz, Katsarkov, Tony Pantev, and Scheffer-Baron, which is the following thing. So S is delta, the unit, let's say, the unit disk in C. I mean, you can cook up a more general statement. X to delta is a non-isotrivial family of K3s. Well, then the Noether-Lefschetz locus of pi is dense in delta. So this is, delta is just a complex manifold, so this is dense for the usual topology. Okay, and so this is the result. This is a prototypical result. So let me give a proof, a short proof of this, which is the original proof. So here is how it goes. Well, the first thing is the cohomology of the K3, as we saw yesterday. As we saw yesterday, it takes the following form. So let's take X, a complex K3 surface. Well, we have H2 of XZ inside H2 of XC, which splits in three pieces, H20, H11, in H02. And so, well, this is 20-dimensional, which is not very important for us, but what is very important is that this is one-dimensional, right? So, okay, so this is all well known, and now we have a non-trivial family of K3. We have an actual deformation. So we have the following data above the unit disk. We have the local system, R2 pi lower star, let's say, well, Z or Q maybe. And when we tensored with the structure sheaf of delta, this has this splits in 3 parts, in H20 plus H11 plus SH02. Okay, so I write it that way. So usual. I mean, this is not. This is of course not a splitting as holomorphic bundles, but this is at least, you know, it's infinity. And we have the Gauss-Manin connection. Okay. So another way to say that, to say that we have the Gauss-Manin connection is that, well, actually we are over a contractible base, so this is just a trivial local system, and we have a varying splitting over delta. Okay. And then, well, the last thing that I need to recall is the local Corollary theorem for K3s, is that since pi is not isotrivial, this implies that the Hodge decomposition, let's say, so the Hodge decomposition above is not constant, let's say. Okay, so this is the only thing that we need. And so how do we use that? So now that we have that, we can give a very short proof by the following thing. So let's consider the following bundle, H11R. So this is, let's say, an analytic real vector bundle of rank 20 over delta, right? So this is not the holomorphic thing. This is just due to the fact that we have a splitting of complex vector bundles, analytic complex vector bundles over real analytic vector bundles over delta. But this decomposition is invariant under complex conjugation. So the middle part actually comes from a real vector bundle, and the total space has, well, dimension 22 over the reals, right? Because, well, the unit disk is a two-dimensional manifold. Okay, so this has the dimension 22, and we also have parallel transport. Okay, which maps H11R to the cohomology of the central fiber. Okay, so this is x0 with real coefficients. Okay, which is also, well, by what is written on the right, this is also 22-dimensional. Okay? So what I just said about the local Corollary theorem tells us that H11 actually varies as a as a local system. I'm sorry, as a I mean, varies compared to the constant local system on the right. And if you unwind what that means, it means that the image, let's say, is open or at least contains a non-empty open subset of H2 x0. Oh, so in particular, well, it contains an open subset of this real vector space, so it contains a point, well, or many points actually, let's say that, many elements of H2 x0 Q, right? Because Q is dense in R. Well, what do these points, so I claim that this is done. Because what do these points correspond to? What do these points correspond to? They correspond to some cohomology class on x0, so some cohomology class on the total space, which becomes of type 1, after modifying the special fiber a little bit, after moving away from 0 just a little bit. And so this corresponds to a Hodge class on some deformation of x0. And so this corresponds to a line bundle on a small deformation of x0. Okay, so this is exactly, so this corresponds to a point in the Noether-Lefschetz locus of pi. Okay, and you have many elements in Q, so you have many of these points. You get the density if you look just a little bit closely. Well, maybe, okay, so I mean, of course, you have to look at points which are not constant here. Right? You have to get rid first of those points which extend to the whole thing. Okay, so that's the result. Okay, so the question is what happens when the base is not the unit disk? What happens if we do arithmetic geometry? Okay, so what happens if you replace delta with a more general base? Okay, so let me focus on one case, which actually will be the one that I deal with more in detail later. So let's take S to be a curve over FQ, and well, let's stay in the same range, the same kind of varieties. So let's take even a simpler thing. Let's take two elliptic curves. So X over S would be E, let's say E cross E prime over S. I'm sorry, two elliptic curves. Okay, so the first thing that one can notice is that things can go wrong even in this simple situation. So the bad case is the following thing. You can take something non-isotrivial by taking E to be a constant supersingular elliptic curve. Okay, and well, E prime non-constant. Maybe the universal elliptic curve or something like that. Well, then the Noether-Lefschetz locus of pi, well, it's going to be this is finite. Okay, so the theorem is false in that case. And why is that? Well, the only way E prime over a point can be isogenous to E is if the fiber of E prime above S is supersingular, and we have only finitely many supersingular curves over a given finite field. Apart from that case, so this very specific case where one of the curves is constant supersingular and the Noether-Lefschetz locus is Zariski dense. Okay, so this is, yes? I'm sorry, what? What is the, so I'm thinking, maybe this is a better way to write it. Just a product of two elliptic curves over a base. Yeah, relative. I mean, I take an elliptic scheme over S. Oh, yeah. Okay. Apart from that, the Noether-Lefschetz is Zariski dense, so this is something that has been proved by Chow and Oort in this specific case, and it follows by essentially so what are you looking at? The Noether-Lefschetz locus of pi in that case corresponds to the point where E and E prime are isogenies, and you can just look at isogenies given by the graph of Frobenius, so purely inseparable isogenies, and so you can essentially compute how many of these isogenies you have in this setting. So you can actually show that you have a lot. Okay, so that's one thing.
I'm a little confused. If E and E prime are both constant and not isogenous, then they're right.
Oh, yeah, okay. Yeah, no, certainly. But I mean, my general hypothesis is that I'm in a non-isotrivial family.
This is supposed to be non-trivial.
So I'm looking at, so my general situation is that I have a family X over S and I study the Noether locus. Of course, if the family is isotrivial, then...
You want both E and E prime separately.
No, I'm saying, so let's assume that E cross E prime is not isotrivial. Then at least one of them is not, right? They cannot both be constant. And the only way, in that case, is one is constant, super singular, and the other is not. Then that fails, and this is the only case where it fails. Okay, so well, I mean, there's a fairly good sense of why this fails. This is because of some ordinarity condition, right? So here is the theorem I want to prove today is the mixed characteristic. And this is the following. So K is a number field. And then E and E prime are two elliptic curves over K. So here I don't need to add an hypothesis of non-isotriviality because, well, I'm not, I mean, no curve over K is isotrivial over OK. Well, then there exist infinitely many places of K, well, let's say OK, where E and E prime are geometrically isogenous. Okay, so that's the theorem I want to prove. So I'll give more comments and consequences of that. So geometrically isogenous means that I reduce E and E prime mod P, but then I need a base change to find over the finite field to find an isogeny. So as I'll explain in a moment, it is very reasonable to expect that this is not necessary, but I don't know how to prove that. Okay, so this is the analog of what happens above. Well, maybe one comment is that as far as I know, the Green-Ogiso result does not, the method does not, that I explained, does not apply at all to this mixed characteristic setting because, well, we don't have parallel transport from one prime to another in this situation. So okay. So I also should say another thing that compared to the Green-Ogiso result, the important thing is that, well, here the underlying variety that we have is something like E cross E prime, and the key properties that we are looking at is that the second cohomology group of E cross E prime has H2 0 equals 1. So that's why this is an analog of that. I mean, the question whether this result holds in greater generality is slightly harder to my knowledge. Maybe so this is very much inspired by geometry, and I'll explain a slightly geometric proof. But I want to give a corollary, which is the following thing. So let again K a number field. And then, well, let's try with a single elliptic curve now. So E an elliptic curve over K. Well, which is not Cn. Oh, well, I'm sorry. An arbitrary elliptic over K. Then one of the following holds. Well, either E has infinitely many primes of supersingular reduction, which is known unconditionally if K has a real place by a result of Locus, or for any K quadratic imaginary, E has infinitely many primes with CM reduction by K. Okay, so if you look at an elliptic curve over a finite field, well, then two things can happen: either it's supersingular, either it's supersingular, or it has complex multiplication by some quadratic imaginary field, right? And if we, I'm not sure exactly what should be conjectured, but if you're optimistic, if you start with a non-CM elliptic curve over a number field and you run through all the primes, all the prime reductions, and one optimistic statement would be that you get each possibility infinitely many times. And so, well, I certainly cannot differentiate between these two things, but well, you get a result in that direction. Okay. So, oh, if E is already a CM curve, then, well, certainly you don't have the second, the reduction of E, either they are supersingular half the time, or the other half of the time they have CM by the same field as E. So, yeah. So you certainly don't get the second case. You don't get all possible quadratic fields, because if it's CM, it's the same CM field.
So you could make examples where there are no supersingular primes.
I'm sorry?
You could have examples where there are no supersingular primes.
What do you? I don't. Are you claiming that, or? No. As far as I know, the first case always happens, but I don't know how.
If you take a Lejeune, y squared equals x minus 1, x minus I over q of I. Right? So the number of points is always divisible by 4.
No, but it's a geometry. I'm talking geometrically, right? So.
All inert primes in your CM.
Yeah.
No, but it's not a CM thing. No, he's talking now about the case where it is.
No, I'm sorry.
Because I think in reply to the question.
I'm sorry. Are you saying that there are elliptic? So this is a geometric statement. Are you saying that there are elliptic curves or a number field K which have no supersingular primes at all?
No, there's a reason Alkes needed a real primes. Or actually, he needed totally.
Well, okay. So, one of the.
Q plus 1 minus AQ. If Q is the norm of a Gaussian prime, it's congruent to 1 by 4. 1 plus 1 is 2.
Mm-hmm.
I
That.
think 0.
No, but even geometry. Okay. Well, okay. Well, anyway, anyway, this is hopefully this statement is correct. So let me just prove this thing, say very quickly how this follows from the theorem. So you just start with E, well, and you so this is you just test it against CM elliptic curve. So start to take a field large K as in the second statement. So this is all a geometric statement, so we can make base field extension as we want. Take E prime to have CM by large K. Then, well, E prime has when you reduce mod P, E prime either is supersingular or has CM by large K. So, well, if E has to be isogenous to E prime after reduction mod prime, then it should be either supersingular or have CM by this by this field. Okay. So let me just give a more number theoretic heuristic as to why the theorem might be true. So let's assume that k equals q. So just for the heuristic. Okay, so we take E and we take E and E prime to elliptic curves over Q, and certainly we can assume that E and E prime are not geometrically isogenious, otherwise the result is trivial. Well then, the only way E and E prime, so E and E prime are isogenous after reduction mod P. Well, this is the same as saying that the trace of the Frobenius of E at P acting on H1 is the same as the trace of Frobenius of E prime at P acting also on the Tate module, right? And these two integers, so these two things are, well, by the Veil conjecture in that case, right? These are integers between plus and minus 2 square root of P, right? And, well, over Q, and if we, I mean, for instance, if we over Q, we have a lot of ideas about how these two integers behave, and we actually know that they behave at random. So they are, so these traces are equidistributed and independent. So in this, so of course equidistributed with respect to the Sato-Tate measure, and independent. So I think in the case of a product of two elliptic curves, it has to be proved by Harris over Q. And so you expect that the probability that E and E prime are isogenous at P is roughly 1 over square root of P up to a constant. Okay? So these are two random numbers between minus 2 square root of P to square root of P. The probabilities are equal is something like that. And well, now, here, the sum of, this sum diverges, so we expect the result. And so as I said before, we expect even a little bit more. We expect that they actually are isogenous modulo infinity many primes. Because of this. We don't have to use to have a base field extension. Okay? Okay, so maybe this is a good time to make a remark that what should we expect for 3 elliptic curves? So by the same reason, this should we still expect infinity many prime by the same kind of heuristic, at least if we are over Q. But the geometric side, on the if you work with 3 elliptic curves now over delta over the unit disk, it's very easy to cook up families of 3 elliptic curves where we don't have isogeny, because just for dimension reasons, the metallurgist Locus has too high of a codimension. So I have no idea what to expect here.
When you say 3, you want them all 3
Yeah.
homogeneous to each other?
Yeah. Yeah. Let's try. Yeah. I mean, yeah. Take three elliptic curves over Q and ask whether there are primes where they are all three isogenies to each other. Yeah, but I mean, just count. I mean, I mean, maybe you have a counter example.
No, but I mean, for the first two to be great, that's a 1 over root k.
Mm-hmm.
But then
The sum of 1 over p diverges.
log.
Okay, so I mean, yeah. I mean, of course. I mean, this is still infinite. That's just my remark. Anyway, but I do agree that it's very slow, but it's still infinite. So I mean, anyway, I don't know whether there should be a geometric interpretation that this sum diverges. That's my question. Maybe. So. Okay. So anyway, maybe let me explain a little bit of the proof. And of course, it will completely break down for three elliptic curves. I mean, that's how. Okay, so, well, this should be the proof. So I want to explain a little bit of this. So this is actually a proof that is much closer to the proof of Borcherdt, Katsarkov, Pantev, and Shepherd-Barron. What did they use? Well, they used the geometry of the Noether left locus in the moduli spaces of K3 surfaces, which is an orthogonal Shimura varieties, and an orthogonal Shimura variety, and the Noether left locus is just a set of special subvarieties which turn out in that case to be divisors. And these divisors have very strong positivity properties due to a famous theorem of Borcherdt, and you sort of leverage that against the geometric situation. So here, I mean, of course, the geometry is much simpler because we are working over x of 1. So for this sketch of proof, let me assume that k equals q, but I really want to emphasize that this is not something that you see at all. So of course, this in all the heuristics that you can cook up in this situation, the fact that you have, I mean, working over Q is very different, but this is a geometric proof, so this is somehow irrelevant. Okay, so we have x of 1, which is isomorphic to P1 over Z. So this is the moduli space of elliptic curves compactified over Z à la Adeline-Rapoport. So we have this. And then E and E prime correspond to divisors, let's say Y and Z, in the arithmetic surface. X of 1, right? And so what are we looking at? Well, we are looking at the Hecke correspondence of x of 1. So we have x0 n, which is, again, the compactified moduli of, let's say, E1 to E2 of cyclic isogenies of order n, right? And this gives us the Hecke correspondences, the Hecke correspondence. Tn, so it corresponds to Tn of by degree En. So let's say, I mean, we can imagine that En is roughly the order of magnitude of n, at least if n doesn't have too many prime factors. And so what are we looking at? So the theorem says the following. That the union over all n's of Tn lower star of y intersected with Z, well, this is infinite. Okay, just as a set. Just we look at all. So this is exactly what it means, right? The point in the intersection exactly corresponds to a finite field and to a cyclic isogeny of degree n between the reductions of E and E prime at that prime, right? Okay, so well, this is pretty clear. Well, I mean, if n equals 1, it means that they're isomorphic, which is okay, I guess. I'm sorry, what? No, I want to prove that they are isogenous infinitely many often. So, of course, yeah, so points where they're isomorphic is as good. Okay, so well, certainly what we assume that E and E prime are not isogenous of a Q bar. So these two divisors and Z have no common component. Okay, so. Oh, I'm sorry. Yes. So these two things have no common components. So of course, I mean, the strategy is pretty clear. I mean, this is very hard to control the set theoretic intersection, but the intersection numbers are fairly, I mean, make sense in that setting. So just a little bit of intersection theory of heights. On x of 1, E of z. So here is what we want to do. So let me add just a little bit more notation. So M, this is J upper star of O of 1. So J maps x of 1 isomorphically to P1. The pullback of O of 1 is the bundle, the line bundle of modular forms of weight 12. Okay, so it has a section which is delta, which corresponds to the section on the right that vanishes at infinity. And, well, this is endowed with the Peterson metric. M bar is the Hermitian bundle with metric. So let me just not make a mistake. So we have delta. So delta is a section of M. This is a pullback of the section that vanishes at infinity. And the metric corresponds to this. So this is delta of tau times the imaginary part of tau to 6. Okay, and so this means that we have a theory of height, and we can compute the heights of divisors with respect to M bar. So then we have the following thing. So I think this was proved by Paula Cohen in that setting, and maybe Pascal Autissier as well has a refinement of this, which computes the height of M bar. So this, in what interests us, this gives us the following thing. The height of the Hecke correspondences, so applied to y. So this is a divisor on the arithmetic surface x of 1, right? So this has a height, which is the arithmetic version of the degree. This is something, so there is a constant, so which is completely explicit, but we don't really care about it, times the degree. So this is the degree of Tn plus a lower star of y with respect to M bar. So there is a geometric part, which is the degree of the Hecke correspondences, of the Hecke correspondence, times log n. Okay? So this is something very nice for us. So let me just explain a little bit, especially since we had a lot of complex geometry. So we are looking at the intersection of these two things, right? If we were over C, over just an algebraically closed field, we would expect this degree to grow like the degree of the correspondence Tn, right? So like En. But of course, we are over Z, so Tn is defined by a polynomial in P1 cross P1. And we have two parameters that help us. We have the degree, but we also have the size of the coefficients of the equation that defines Tn. And this is what accounts for the log n, which helps us a lot. And so, of course, this height of Tn lower star y with respect to this line bundle can be computed by, well, a very specific section of the line bundle, which is given by Z. So this means, so if we phrase that in terms of intersection numbers, we have the following thing. The height there is going to be controlled by two things. First, a suitably weighted intersection number, so the degree of Z intersected with Tn lower star of y minus something like, okay, so I will explain notation in just a second. So this is the hierarchy of degree. That's the hierarchy of intersection number. And this is some Archimedean term. And this, as a whole, is still C n log n. So what are the terms in our? Oh, yeah. You mean here? Yeah, of course. Okay, so let me explain what the terms are. Let me write down the term. Okay, so first, this degree, so the degree of something like sum of ni pi, if I take a zero cycle on x of 1, this is just the sum of ni log of the cardinal of the residue field of pi. And what is this thing? Well, this is the exact same number in the Archimedean setting. This is, so when I write Sz, this is a section of O of 1 that vanishes at Z. So Sz of tau is the following thing. So I want to take a section that vanishes exactly at Z. So this is Z. Let's recall that Z is the divisor corresponding to the elliptic curve E prime. So this is T minus, I'm sorry. This is J of E prime minus J of tau delta tau. Okay, so this vanishes exactly at J of tau, J of E prime, and we pair that against the Hecker orbit. Okay, so what do we need to do with that? So we want to show that there are lots of intersection points of Z and Tn lower star of Y. So there are lots of isogenies at a lot of different points. So we know how to compute the intersection numbers, at least to estimate the intersection numbers. This is something like En log n. So what do we need to do? We need to show that the local intersection numbers are very low. Okay? So the goal now is show that the local intersection numbers are, well, very low in the sense that they grow in a slower way than en log n. That's exactly what you need to show, right? So you need to show, so let me leave this vague statement right here, but you need to show that if you take a finite number of places, including the Archimedean place, then you can find infinity many n such that all these intersection numbers of all my given finite set of places is smaller than en log n. So let me first say that this is, at first view, a reasonable thing to ask because if you concentrate on one place, then this is a geometric situation, so you expect a growth like en, not en log n. So log n is really the global factor that sort of helps you work that out. Oh, the local okay. So this is so the local intersection numbers are both the Archimedean term at the place at infinity, and then well the local things are the ones that lie above a given place. Okay, so this splits into a sum over all places of K, of Q here, all prime numbers. Okay, so we have to work prime by prime. Okay, so let me work, let me work prime by prime. So, so one final, before explaining the proof, maybe one final heuristic which explains exactly what remains, what needs to be proved, and what is easy and what is hard. So let's look at the Archimedean term. Okay, so the Archimedean term, so this is Sz applied to the Hecke orbit of y. So this is the following thing. We write Tn lower star of y. This is, let's say, j of tau 1 plus etc. plus j of tau en, right? So this is just the j invariance of all the elliptic curves that are isogenous to E by an cyclic isogeny of degree n. Okay, and then, so Sz, so the Archimedean term is the following thing. This is the sum over i's of the log of Sz. So this is the sum of the log of, so we have j of E prime minus j of tau I times delta tau I times, well, the imaginary part. Okay, so that's what we get. So this is a Riemann sum. And so how can we have an idea of what this looks like? Well, we know that the tau i's are equidistributed in the Poincaré half plane, let's say. So this is a result due to Clausel O and Ulmo, right? The graph of the Hecke correspondences are equidistributed, and so this. So we need to compare the Archimedean term to, well, so we have En terms, so this is to be compared to En times the integral over, let's say, x of 1c of, well, log of, forget anything, right? So j of E prime minus j of tau delta. So imaginary part of tau to the 6 dx dy over y square, right? So tau is x plus iy, and so this integral converges, right? So there is, there are two singularities. Well, there is singularity at infinity, which converges, and there is a singularity when tau goes very close to E prime, which is also integrable, right? So this is, this is a reasonable thing, right? The way this this integral is very high, tends to be very high at the point tau, where tau, j of tau is very close to E prime, which means exactly that some curve isogenous to E prime is very close in an Archimedean way to E, right, up to isogeny. Okay, so this puts, let's say, a more quantitative heuristic behind all this computation, which is exactly the equidistribution of the Hecke correspondences on x of 1 cross x of 1, which lies at the heart of this. Well, of course, this is not enough. Why is that? Because we are not integrating a smooth function. Right? Even though the toi's are equidistributed in the plane, and even though this integral converges, it might still happen that for a single I, let's say, a single tau I, well, j of tau I minus j of E prime, well, this could be very, very small. So, of course, equidistribution does not tell you that you can approximate the integral of any function. Right, and so okay, so let me back up a little, and then I'll explain all the pieces that need to be fit together. So, okay. So we want to control all the terms of this sum and show that they are way smaller than E n log n. So. So let's sum up. So we need to control all local terms. Okay, so we have a bunch of them. So first we have the points of multiplicative reduction, where one of the elliptic curves has multiplicative reduction, but this is fairly explicit, right? So we're looking with isogenies of a curve with multiplicative reduction at a prime, but then we write it as we have a uniformization by the Tate curve, and then the computation of the term here. It's fairly explicit. It's fairly easy to control and to show what you want. Okay, then you have the point of good reduction, or the Archimedean place. Right, and at all these points, well, you need to control these kind of sums, right? So this is the Archimedean one, but the non-Archimedean one is exactly has a very similar form. So you need to do two things. Well, you need to check to compare a Hecke orbit to a given point in x of 1. So you have most of the points that are taken care of by equidistribution. Of Hecke correspondences, this takes care of most points in Tn lower star of y. Okay, so in the Archimedean setting, this is this theorem of Clausel, Owen, Ulmo. In the p-adic setting, this is the only result that the equidistribution result that one might need has been proved by Farg, but I think this is unpublished. But you can actually get by with very, very weak results. I mean, this is not, you don't need something of very high precision. And then you have the worst approximations. Okay, so which in the Archimedean terms take the form of controlling this specific thing. So can it happen that a lot of the Hecke orbits of a given point all sort of have very good approximation to a single point index of 1. So this is, I mean, this is a slightly strange problem, at least to me, because this looks like a Diophantine approximation problem. Then, I mean, in a way, you start with two things that are defined over Q, so of course their J invariant might have, I mean, it's hard to control the height of the J invariant of the of elements of the Hecke orbit. So there, I mean, forms of the Roth theorem or anything like that do not give you a satisfying estimates, but there might be a way to see rather directly that this cannot be too small compared to n. But let me explain a very cheap trick to find reasonable to avoid this kind of thing. So here is the trick that I want to explain. Let's say two good approximations. Okay, so assume, so start with n. Fairly large. Okay, so we have E and E prime, so assume, so we have two things, right? If for all cyclic subgroup C inside E of cardinal n, of order n j of E minus j of E prime, j, so these two things are, well, bigger than some epsilon. If they are not too close, well, then we're done, right? That's what we want to do. Well, okay, so if we take n at random, if the approximations are not too good, then, well, nothing happens, we are good. So, well, assume that this does not happen. So we have Cn, some cyclic subgroup of cardinal n, and this is very, very small. J of E mod Cn and J of E prime are very, very close. So here, I'm sorry, epsilon. So these two curves are very, very close for at some place, right? Okay, so let's take n prime. So let's take n1 and maybe let's take n2. Okay, so n2 is another, let's test against another class of isogenies. Maybe n2 is roughly the same order of magnitude as n1, and well, maybe we're in luck. And j of E mod C2 is actually also very, very small. Well, that can happen. But we know, well, there is only one way this can happen. The only way this can happen is if both E and E prime are very close to CM curves. So this implies that E and E prime are very close to CM curves, right? The only way, because if you have something like that, this means that E has almost a self-isogeny of degree something dividing n1 times n2. But then, but CM elliptic curves, well, certainly cannot be too close. To one another. Right, because I mean, they correspond to points in the Poincare half plane with quadratic coefficients. And they cannot be too close for the Poincare metric, just for height reasons, for basic height reasons. So this case is also very good for us, and that's essentially what you use. Okay, so maybe one last remark. So as I said, I mean, this is something about equidistribution of Hecke correspondences in a slightly, I mean, an application of this kind of well-known ideas. There is one phenomenon that I have no idea how to see using this kind of method, which is methods that come from parity, right? If you start with a slightly different situation, maybe with a K3 with pk number 1, now over Q, and you start looking at what happens when you reduce mod P, well, then by the Tate conjecture for K3 surfaces of a finite field, then the pk number always has to jump. So we have something that is way different from this. We don't expect, I mean, we have a parity well, a parity phenomenon that happens. And I just wanted to stress that this is, I mean, I have no idea how to see this phenomenon geometrically, even constructing the cycles on the reduction or seeing it, of course, with this kind of geometry of the Noether-Lefschetz locus. There is a huge part of the geometry of the Noether-Lefschetz locus in mixed characteristics that seems very hard to understand. Okay, thank you very much.